Hey guys, so in this video I'm going to start with local extreme points, which is exercise 17.4, and in this video I'm going to discuss theorem 17.5. I'm going to write it down and I'm going to explain it a bit. Then for this video, for watching this video, you should have the knowledge of Hessian matrix, negative semi-definite, positive semi-definite, right? So it'll help you a lot. And then come to this video, start solving questions with me, or just see the solution, right? So let's just start now. Hi, so this is theorem 17.5, second derivative test for function of two variables, right? So let fx comma y be a function with continuous partial derivatives of the first and second order in a domain S, and let x naught comma y naught be an interior point of S that is a stationary point for f. So what they are saying is, let fx comma y be a function with continuous partial derivatives of the first and second order in a domain S, and let x naught comma y naught be an interior point of S that is a stationary point for f. So basically this theorem is talking about the conditions when you can prove that the point that you have is a local max or a local min, right? So first of all, what we'll be doing is we'll be taking out the stationary points, and the method for taking out the stationary points is by equating the first order partial derivative with respect to all the variables equal to 0, and from that you get the stationary points. Then you have to also check that the stationary points are interior or not, and in most of the cases they turn out to be interior, right? After that, what you have to do is you have to find the second order derivative, second order partial derivative. In this case you have to you have to find a second order partial derivative. In the previous case, when you were finding stationary points, you had to only find out the first order partial derivative, right? So if I just explain it here, so our first order partial derivative is first order so my first order partial derivative is this gives us the stationary points, interior stationary points. I'm assuming that the points that we get is the interior stationary points, and let me write the interior stationary point as x naught comma y naught. Now what you will be doing is you will be finding the second order partial derivative. Second order partial derivative will be del f x comma y del square. So right, this is f of 1, and this is f2. This is written as f2. So if I write it here, f1 is del f by del x, and f2 will be del f x comma y by del y, because y is the other variable, so we represent it by 2, right? So now this is f11. Why? Because this is d by dx f of 1, right? So this is written as f of 2, f of 1 comma 1, f of 1 comma 1. Now similarly I can write f of 2 comma 2, sorry, f22. So d by dy del fx comma y by del y. This is also written as del square fx comma y by del y whole square, which is equal to f of 2 comma 2. Right? So let me just draw boxes around this. I'll just, I have to make sure whatever I am writing is clearly there in my PDF, because what I usually do is I share my PDF, and if some of you try and open that PDF and try to go through it, you should make sense of what has happened in the video and what did I do while solving the question, right? That is why I'm trying to make it as neat as possible. Right? So now let's just move on. Now let me go back to my theorem. So what was this theorem saying? So basically, let fx comma y be a function with continuous partial derivative of the first and second order in a domain S. Yes. So I was explaining you the second order partial derivative, right? So after you have found this, this expression f11 will be this expression will be in variables, right? Now what you will be doing is you will substitute your stationary point, which is x naught comma y naught, inside the expression, right? And you will be getting a value as a. Now similarly, what you will be doing is f22 x naught comma y naught, you will substitute your interior stationary point, and you will be getting b, right? Now one more thing. This was the second order partial derivative with respect to x. This was second order partial derivative with respect to y. Now cross partial derivatives are del f x comma y by del x with respect to del y. So this is del square fx comma y by del y del x, and this is equal to this f1 comma 2 is always equal to f2 comma 1 by Young's theorem, right? You have to study the previous chapters if you are finding if you are experiencing any confusion in all of these concepts, right? You have to study the previous chapters like chapter 15 and chapter 16. So del f21, which is del by del x del fx comma y by del y, this is again equal to the same expression, right? Del x into del y, which is f of 1 comma 2. So basically f of 2 comma 1 is equal to f of 1 comma 2. Right? Hmm. So now, and this is equal to f2 comma 1 is equal to 1 comma 2. Here in the theorem they have written this as. Now when you will be finding out this, this again will be an expression, with two variables, right? X or y, or simply x. So what you'll, or simply y, what you will be doing is you will be substituting your interior stationary point in this, and you will be finding out a value, you will be getting a value, right? And the value will be equal to c. So what I am just explaining what they have done in the theorem, right? So I've clearly, wait, this is b, they have written this as b, this is b, and this is, wait a minute, this is c, sorry. So this is c, this is a. After you have found out the second order partial derivative with respect to x and you substitute the interior stationary points, you get a. After you have found out the second order partial derivative with respect to y, you substitute your stationary point, you get c. And after you have found out your cross partial derivatives with respect to x and then y, or then x, both are equal, and you substitute your interior stationary point, then you get b, right? So now going back to our theorem. So now this is this theorem is saying that a, we have a, this is a, this is b, and this is c. So the theorem says that if a is less than 0 and ac minus b square is greater than 0, then x naught comma y naught, which was our interior stationary point, is a local maximum point. These are the conditions. What we'll be doing is we'll be following the process. We'll be finding the interior stationary points, we'll be finding the second order partial derivatives, and after that we'll be denoting them as a, b, or c, and then we'll be applying these conditions. Then the second condition says that if a is greater than 0 and ac minus b square is greater than 0, both are greater than 0, then x naught comma y naught is a local minimum point. And the third condition says that if ac minus b square is less than 0, then x naught comma y naught is a saddle point. And the fourth condition says that if ac minus b square is equal to 0, then x naught comma y naught could be a local max, comma a local min, or a saddle point. So this is a special condition. In the case that this condition arises, we would have to manually put in the points around the interior stationary point and check if this is actually a local maximum, minimum, or what. Now you would have to go through the definitions of what is local maximum, local minimum points, but I'll be explaining these briefly. What is local maximum, local minimum points? Again, my duty was never or my purpose of making these videos were never to explain you guys the concepts. My purpose of making these videos was to bring in the questions, put in the solutions, so that when you guys have studied through the book, have gone through the text, then if you want to solve the questions and you encounter any problem, or you just want to see the solutions and see the process of how I am solving it for more clarity, then you can come to this channel. But while solving the questions, I feel I need to explain certain things, so that if you haven't even started reading the book, you wouldn't understand a thing of what I am doing right now, right? So that's the reason why I need to explain certain concepts and certain points. But I'll be explaining all of these very briefly. So don't expect this to be a lecture on how to learn the whole process of what and how things are happening. For that, you have to open the book and start studying, right? So if I now explain what is a local min and a local maximum point. So basically, what happens is, if I have a point which is x, and if I have a point x naught which is in the boundary of x, so basically x naught can be here also, x naught can be here also, but it is very near to x, our point that we are talking about. So basically I am saying that x minus x naught, which is the difference, which is the distance between the 2 points, is less than delta. Which is less than delta. And what I'm saying is fx is greater than fx naught for all x minus x naught less than delta, right? This shows that we have a local max at x, right? So I have to explain this first. So x minus x naught mod. So basically if I have 2 points, so this point is -2 on the number line. If I have 2 points, -2 and -3, so this is my number line. And if I have 2 points, -2 and -3, and if I try to subtract the 2 points, so this is my x and this is my x naught. So if I just subtract these 2 points, I'll be getting to find the distance between them, I'll be getting -2 and -3, which is -2 plus 3, which is +1. So I didn't need mod here. Wait a minute, let me just change this a bit. So wait a minute, I'll be taking a different example. So if I have 2 points, this is my x naught and this is my x, and there are 2 ways to find the distance here, right? So first method will be to subtract x minus x naught, which is x minus x naught, which can be 4 minus -6, which will be 10. Or I can do is what I can do is x naught minus x, which is x naught minus x is -6 minus 4, which is -10. Now distance can never be negative, so what we do is we put a mod sign. We put a mod sign and we get 10, right? And also we don't know if x is greater than x naught or or x is greater than x naught or x naught is greater than x. So the case could have been like this also. It could have been like this also, that this is x naught and this is x, and now x minus x naught turns out to be negative, right? So this is negative, so this is negative, right? And that's why we put a mod, because we are measuring the distance and distance is always positive, therefore we put a mod. Now in practice, x naught and x won't be this far, because we are talking about local maximum and local minimum points. And when I'm talking about this expression, that x minus x naught is less than delta, so delta is any number which is tending towards 0, which is very close to 0. What this means is that x minus x naught, the distance between x minus x naught, so I have explained you that x minus x naught is the distance, so x minus x naught, the distance, is less than delta. What this means is, and delta is moving to 0, this means that the distance is very close to 0, right? So when I write less than delta, so delta can be 0.1, delta can be anything. Delta can be when delta is moving to 0, delta can be a very small number. So delta can be this, delta can be equal to, let's just say 0.000001. So what this means is that x minus x naught, the distance between x and x naught is less than 0.00001. So what we can say is that these 2 points are very close, because the distance is very less between the 2 points, right? So that is what we mean as local. This expression, when I write this expression as this whole expression, wait a minute, I need to remove this box. This whole expression signifies what we mean by local. This tells us local. This explains us what is local, right? And now I'm saying fx, x minus x naught, which is less than delta, and delta is going to 0, so the 2 points are very close. Now I'm saying is, for any x which is close to any x naught, fx is always f of x is always greater than f of x naught for all x minus x naught less than delta, where delta is going to 0. Now what this means is x minus x naught are 2 points which are very close, so they are local, and fx is always greater than fx naught, so there are 2 points x and x naught, and the value that fx gives is always greater than fx naught, and the 2 points are very close. What this means is this shows that we have a local max at the point x, because these 2 points are local, x and x naught are local, and fx is always greater than fx naught. Therefore we see that local, and we know that max, so we join both of these terms and we find fx greater than fx naught for all x minus x naught less than delta, where delta is moving to 0. This shows that we have a local max at x. Similarly, what I can write, I can write the definition of local min. So if I write the definition of local min, let me just put 1, this is 2. So if I just put in the definition of local min, fx less than fx naught, fx less than fx naught, I hope you guys can see. I don't think the brightness is. Just give me a minute. Right. So fx less than fx naught, right? Fx less than fx naught for all x minus x naught less than delta, and delta is going to 0. This shows that, and x and x naught are just two variables, right? Random points. This shows that we have a local min at x, at point x. Now I've explained you the definitions. Now I've explained you the theorem in the best possible way that I could, and I explained you what is first order partial derivative, second order partial derivative. I didn't mean to explain you guys these concepts, because these concepts are already present in the previous chapters, before chapter 17, in chapter 16 and 15. So you have to kind of see those chapters to understand what is happening, right? And now moving on to an example. So also let me just explain you guys this. What this means is, so when we say that a is less than 0 and ac minus b square is greater than 0, how are these conditions coming up? When I'm writing a is less than 0 and ac minus b square is greater than 0? So this was when I was talking about a single variable. This was when I was talking about a single variable. This whole explanation was only to explain you guys what local min and local max means, right? So now ignore this, right? So now this question must have come in your mind, that when a is less than 0 and ac minus b square is greater than 0, then x naught comma y naught is the local maximum point. And why is this happening? This is happening because when I create a Hessian, so this is a Hessian matrix, x naught comma y naught, right? So this is a Hessian matrix, and now you have to study the book for what Hessian matrix is and how is it created and what are quadratic forms. All of that you have to go through the book and understand. For that you have to go through the book, but I am going to explain you the conditions once. So the Hessian matrix, when we have a two variable Hessian matrix, what this says is that you write the second order partial derivative with respect to x here, so Hessian matrix, if I just draw Hessian matrix, So here I'll be writing f11 x naught comma y naught, f12 x naught comma y naught, f21 x naught comma y naught, and f22 x naught comma y naught. Right, now the condition says that if after putting my interior stationary points in the Hessian matrix, I get f11 x naught comma y naught, which was equal to a, as greater than 0, and I get f11 x naught comma y naught into f, basically the determinant f22 x naught comma y naught AC minus b square. So f12 is equal to f21. So I can write this as 12 x naught whole square, because these two are also multiplied, right? Just finding the determinant, whole square, right? So what this means is, this is a, this is c, and this is b, right? So this says that AC minus b square. So a greater than 0 and AC minus b square greater than 0 implies we have a local max, right? And what this also means is that the Hessian matrix is a Hessian x comma y, x naught comma y naught, because all of these conditions, this is greater than 0 and the determinant is also positive. What this means is that the Hessian matrix is a positive definite matrix, and when I have A as, so I've explained you what is A, what is B, what is C. So if A is less than 0 and AC minus B square is greater than 0, we have negative definite matrix. So H, which is the Hessian matrix, is a negative definite matrix, negative definite matrix, right? So this is basically the determinant of the matrix, and this is the first term of the Hessian matrix. So first A11 of a matrix. If I write a matrix as A11, A12, A21, and A22, if I denote a matrix as this, so this is my A, and this is my B, this is also my B, because 21 is equal to 12, and this is my C. So A is greater than 0, AC minus B square, which is the determinant, is greater than 0, so positive definite matrix. A less than 0, AC minus B square, greater than 0, negative definite matrix. If A greater than 0, AC minus B square less than 0, indefinite, or I would say a saddle point. Saddle point is basically when we find a saddle point and we look at it on a graph, what we find is that from one angle it looks like a local max, and from other angle it looks like a local min. From one angle it looks like a local max, and from one angle it looks like a local min. So we can't really say if it's a local max or a local min. So basically then we classify that kind of point where we can't say anything about that point, right? So it is not a local min or local max. So then we say that it is a saddle point. So now this is also, and if I have A less than 0 comma AC minus B square less than 0, then also saddle point. So whenever my determinant is less than 0, I say that it is a saddle point. I've written the conditions for saddle point. So I am not writing these very neatly. This was just to explain you guys what does this mean. what does the Hessian matrix mean, and what is positive definite, what is negative definite, because I'm going to solve like this only, using a Hessian matrix, right? So whenever we have a negative definite, we get a local max. Wait a minute, I made a mistake. Here it is local min. Whenever my a is greater than 0 and my ac minus b square is less than 0, we get a local min. And whenever I have my negative definite, we get a local max. So when my a is less than 0 and my determinant is positive, I get a local max. Yeah, so my a is less than 0, ac minus b square is greater than 0, local max. And my a is positive, ac minus b square is positive, you get a local min. Now let's solve the question. Wait a minute, let's solve one example in this video, and then I'm going to take up questions from the next video, because this video has become quite long. So example, I would take up example 17.9. Let's just solve example 17.9. Example 17.9, page 633 of my book, Sydsaeter and Hammond, Mathematics for Economic Analysis. Right, so let me just zoom in a bit. Now let's just change the ink. Find the stationary points of fx, y and classify them when we need to find the stationary points and then we have to classify them. So fx, y is equal to minus x cube plus xy plus y square plus x. Minus x cube plus xy plus y square plus x. This is my stationary point. So f of x is minus 3x square plus y plus 1. My f of y is x plus 2y plus 0. No need to write 0. I'll equate these to 0 to find my stationary point. So this will give me y plus 1 is equal to 3x square, or y is equal to 3x square minus 1. So if I just substitute this in the second partial derivative, sorry, this is the first equation, this is the second equation. Now I'll substitute this in 2. So I'll be getting x plus 2 times 3x square minus 1, which is equal to 0. So 6x square plus x minus 2 is equal to 0. So this gives me 6 into 2 is 12, 4x minus 3x, which is x, and 4 into 3 is equal to minus 12. So 6x square plus 4x minus 3x minus 2 is equal to 0. If I just take 2 common, 3x square plus 2x minus 1, 3x plus 2x common. Right, so I get 3x plus 2, 2x I have taken common, so I get 3x plus 2 minus 1 is common, 3x plus 2 is equal to 0. What I get is 2x minus 1 into 3x plus 2, which is equal to 0. And from here we can say that x is equal to half, comma, x is equal to minus 2 by 3. Now if I just substitute this expression in this, now if I just substitute these values for x in this expression, I'll be getting the values of y, the distinct values of for y. So I'll be getting y is equal to 3 times the square of x, so 1 by 4 minus 1, so 3 by 4 minus 4 by 4, which is minus 1 by 4. Y is minus 1 by 4. when my y is 1 by 4, y is 1 by 4 when my x is equal to 1 by 2. Similarly, my y is equal to 3 times the square of minus 2 by 3, and this is minus 1. This is minus 1, which is 3 times 4 by 9. 4 by 9, right? 3 and 3 gets cancelled, minus 1, so I'll be getting 4 by 3 minus 3 by 3, which is 1 by 3. 1 by 3. So from here I can say that y is equal to 1 by 3 when my x is equal to half. My x is equal to minus 2 by 3. So my two stationary points are right. These are my two stationary points. Now I need to classify them. Let me check if there are only two stationary points or they have found out more. Yeah, we have found out the stationary points correctly. So now we need to classify them. For classifying, I'll be using my Hessian matrix. So now I'll be finding my second order partial derivative with this, which is fxx, which is minus 6x plus 0, and fyy is 2, right? So my second order partial derivative, or f11 or fxx, is equal to minus 6x, and my f of y comma y, or f of 2 comma 2, f of 2 comma 2, f22 is equal to 2. So now my cross partial derivative with this, which is equal to f12 or f21, so I need to just, either I need to find the partial derivative of fx with respect to y, or I need to find the partial derivative of fy with respect to x. So let me show you one thing. So f of 1 2 is f of 1 2 is, so f of 1 2 will give me minus 3x square plus y plus 1. So I'll be finding the partial derivative of f of 1 with respect to 2, which is partial derivative of f of x with respect to y. So this will give me 1. This will give me 1 because only one term of y is here, and f of 1 will give me 1 because only one term of x is here. So I'll be getting 1. Basically f of 2 is equal to f of 1, which is always true using Young's theorem. You can read more about this theorem in the previous chapters, Young's theorem, right? After doing this, now I have found out my partial derivatives, right? My second order partial derivatives and my cross partial derivatives, I have found them out, right? So So now what I'll be doing is I'll be creating a Hessian matrix of fx comma y, and this is equal to minus 6x 2, this was equal to 1, so 1 and 1. This is my Hessian matrix. Now what I'll be doing is I'll be substituting the value of my stationary points. So my first stationary point was half comma 1 by 4, half comma 1 by 4. Yeah, so half comma 1 by 4. Now I'll be substituting this half comma 1 by 4. So if I substitute half in this minus 6x, I'll be getting minus 6 into 1 by 2 minus 3. So minus 3, 1, 1 and 2. So I can say that my a, which is my minus 3, a is equal to minus 3 is less than 0, and my determinant which is ac minus b square, because this is my b, this is my a, this is again my b, and this is again my c, right? So my ac minus b square, which is my determinant, is equal to minus 3 into 2 minus 1 whole square. So this gives me minus 6 minus 1, which is minus 7. So my ac minus b square, which is my determinant, is minus 7, and the condition that we had is the third condition. The third condition says that if my ac minus b square is less than 0, then x naught comma y naught is a saddle point. So my 1 by 2 comma 1 by 4, so my 1 by 2 comma 1 by 4 is a saddle point. Saddle point is, you can also imagine a saddle, a horse saddle, right? You can also imagine that, the figure of that horse saddle, on which saddle is, I guess, the structure on which we sit while we are riding a horse, right? So I don't know exactly if that is the exact meaning of saddle, but yeah, you can imagine its shape if that's the actual meaning of this word, right? And you can imagine how a saddle point will look like. So now what I'll be doing is I'll be using the second point. So h of half comma 1 by 4. Now I have h of my second point was this minus 2 by 3 comma 1 by 3, minus 2 by 3 comma 1 by 3, which gives me minus 6 into minus 2 by 3, minus 6 into minus 2 by 3, minus 6 into minus 2 by 3 will give me 3 2s are 4. So here I'll be having 4 1 1 2. So here my a is which is my first term, is equal to 4, which is greater than 0. My ac minus b square, so this is my b, this is my b, this is my c, this is my a. So ac minus b square gives me this is 1 2, this is 4. So ac minus b square, this is 4. So ac minus b square gives me 8 ac minus b square 1, which is equal to 7. 0.28 minus 1, 7. So 7. This is also greater than 0. So my a is greater than 0. My ac minus b square is greater than 0. This implies that I have a local min. Earlier I had made a mistake while I was explaining you guys. So I corrected the mistake afterwards. So this is a local min. So my minus 2 by 3 comma 1 by 3, minus 2 by 3 comma 1 by 3 is a local min. Now you can check this on page 633 is the question, and page 634 is the solution, so you can check that out. So 1 by 2 comma 1 minus 1 by 4 is a saddle point. So this was minus 1 by 4, right? Oh, wait a minute, this was minus 1 by 4. This has not made any difference to our solution, but yeah, this is minus 1 by 4. I also found out minus 1 by 4 here. Here I found out minus 1 by 4, but I forgot to write the minus sign. Thankfully, we didn't have to substitute y in this question because the second order partial derivatives and the cross partial derivatives were independent of y, but and the second order partial derivative of x was also independent of y. But yeah, thankfully we got saved. Otherwise, I would have to solve this question again. 1 by 2 comma 1 minus 1 by 4 is a saddle point. This is right, and minus 2 by 3 comma 1 by 3 is a local min. So you can check this out on page 634, right? So thank you so much for watching this video. This video was quite long. I must have made some mistakes in explaining you some concepts, right? So I had to correct myself again and again at some point. Thank you so much for watching this video. I hope you guys like this video. If you have any comments, if you find any faults in my explanation, if you think that something I explained and you guys couldn't quite make sense of it, do let me know, right? Thank you so much, and please subscribe the channel, share the video. It encourages me to keep on putting in more videos, right? Bye bye.